Ready to start now. So basically, Eddie's sick this week, so I'm going to be teaching 2 weeks in a row. And I'm sorry, like I didn't get much preparation, so I might make some like mistakes in class. All right, so today we're going to be working on some basic like geometry skills. That involves like basic area formulas like Pythagorean theorem and like some now don't worry guys, it's not corona. Don't worry guys. Okay. So some like basic angle formulas and stuff like that. So we're gonna start. Oh, because I live in Florida. That's why I'm in Eastern time zone. Okay, so we're gonna start by discussing parallel lines. So we're just gonna go over the most basic angle properties of parallel lines. So if you have two parallel lines, what that basically means is they go on forever without ever touching. So if you can imagine, these two lines will never touch. And if you have a transversal line that crosses both of them, there's some cool angle properties that you can find. You can find that this angle right here is equal to this angle, which is equal to this angle. So all the angles I'm highlighting are equal from parallel lines. So those are that's basically all you need to know for parallel lines. Right? This will be used later on in the future. So everyone gets why this is true, right? Hey, just making sure everyone knows that. Okay. So one useful formula to know is the sum of interior angles of a polygon, of a convex polygon. Angles. So a convex polygon is basically anything which angles their interior angles are not greater than 180. So for example, we can have like a pentagon right here, and that would be considered convex. Something that's not convex would be like this shape or something, because one of its interior angles is greater than 180 degrees. There's a nice formula that Hansen already put in the chat. The sum of interior angles of a convex polygon with n sides is just n minus 2 times 180 degrees. And there's a really nice way to prove this formula. So let's just start off with a triangle first. Let's just say we have a random triangle like this. Let's call it ABC. So using this formula, the n minus 2 times 180, we have that these three angles, I'll just use different colors. These three angles should all add up to 180 according to the formula. And we can prove this using a cool parallel line method. We draw a parallel line passing through A that's parallel to BC. So if we draw this line right here, so that's parallel to BC, we have that this angle Oh shoot, that's the wrong color. Oops. We have this angle is equal to angle ACB, or like the two blue angles are equal, because we have that the two lines are parallel, so that these two angles should be congruent. And using the same exact logic, we can determine that this angle is also equal to this green angle right here. And if you see that these three angles are going to add up to a straight line, which is 180 degrees. So this is just simple proof for a triangle having 180 degrees. And we can extend this to larger polygons. So say like we just have like a polygon with 5 sides, or a pentagon, a random pentagon. And let's just call it A, B, C, D, E. What we can do is we can just connect this point A. Let's connect lines with all the other vertices, like that. And what you can see is that we have formed 3 triangles. And if we sum up the angles of all 3 triangles, we get the sum of the angles of the whole entire polygon. So if a polygon has n sides, doing this method will result into n minus 2 triangles. And then n minus 2 triangles, we know that each triangle is exactly 180 degrees. So the total sum of all the angles is just simply n minus 2 times 180. Everyone gets that, right? Okay, good. So next, we're going to go into the Pythagorean theorem. I mean, this theorem is pretty basic, so I'm pretty sure all you guys already know it. But I'm just going to go ahead and review it. The topics we cover are going to be pretty easy, but the questions on the AMC might get pretty hard. So we'll get to some problems, and you can see how to apply these. Pythagorean theorem just states for any right triangle, let's call this side length A, this side length B, and this side length C. We have A squared plus B squared equals C squared. Oh, and this angle has to be right. It has to be a right triangle. So like one easy proof is like, if we take one of these triangles, call A and B. Let's draw 3 more of these triangles in this fashion. Oops, just pretend like they touch. This diagram's so bad. Okay, so from this, we have the area of each of the blue triangles. Oh, I haven't gone over this, but the area of a triangle is simply A times B over 2. So the area of this blue triangle will just be AB over 2. And since there's 4 triangles, 4 of these blue triangles, we multiply the area by 4. And then we have this green square right here. And the area of the green square is just c squared. And then we have the sum of all those areas is going to be the area of the entire square, which is going to be a plus b squared. If we expand this side out, we'll get a plus b squared is just a squared plus b squared plus 2ab. But we notice that this is equal to 2ab, and there's 2ab on this side. So if we cancel both of them, we're just left with c squared equals to a squared plus b squared. And this is probably like the most used, or if not one of the most used theorems in like AMC and like math counts and stuff. Wait, how do you spell Pythagorean? I'm probably gonna mess up. I'm gonna be honest. I'm probably gonna mess up. Pythagorean theorem. Something like that. Okay. So that's the basic proof of the Pythagorean theorem. There's actually like a lot more proofs that you guys can look into. I think there's like thousands of Pythagorean theorem proofs, and it's kind of interesting. Okay. So the last thing we're going to cover are the basic area formulas. So the first basic figure is a rectangle. I'm just going to speed through these because these should be pretty easy. Side lengths of A and B, area is just A times B. If we have a triangle, what we do is we look at the base and its height. Its height is defined as the other point, and you draw a line perpendicular to the base. So that length h will be the height. So h times b. This might be more difficult for like if you have like an obtuse triangle. If this is the base, you do the height the same way. You just extend this line and you draw a perpendicular down to the line. This is like the area of a triangle formula. Wait, this makes sense to everyone, right? Oh, it's over 2. My bad. Yeah. Oops. Yeah, you multiply them and divide by 2. Okay, so if we have a rhombus, the definition of a rhombus is that all 4 sides are the same. So we have like this side equals this side equals this side equals that side. So the area of a rhombus is you look at the 2 diagonals. Let's call them the length of that be d1 and the length of this diagonal be d2. The area of the rhombus is just d1 times d2 over 2. For a parallelogram, where like the opposite sides are parallel, if this length is b, would that be the base? And the distance between the sides is h. The area of the parallelogram is just b times h. And this information is like really basic, but it should be enough to solve most of like AMC8 and like math counts geometry questions. You just have to get familiar of using like all of these tools. Okay, I think we can get to some basic questions. This one's a 2014 AMC8 number 14. There's no diagram, so I'll draw it for you. It says rectangle ABCD and right triangle DCE have the same area. They are joined to form a trapezoid as shown. What is DE? And let me just pull up the diagram real quick. Okay, so what they tell us is that rectangle ABCD and right triangle CDE have the same area. So first, let's find the area of rectangle ABCD. That's just simply going to be the base times the width, the length times the width, which is just 30. So we have 30 is also equal to the area of triangle CDE. And we also know that the area of CDE is just equal to the length of CD times CE divided by 2. Yeah, everyone has the answer already, but I'll just go over it in case someone needs help. So we have CD, since it's a rectangle, we have CD equals 5. So we have 60 equals CD times CE. So we get that CE is equal to 12. Right? And now we have two legs of a right triangle. So that just tells us to use Pythagorean theorem. And if you do enough, you'll just memorize your triples. You'll just recognize that 5 squared plus 12 squared is equal to 13 squared. So DE is just simply equal to 13. Okay, everyone gets that, right? I mean, it's on the AMC8, so like number 14 shouldn't be that hard for you guys. Yeah, number 14 is not that bad. Okay, so this is just like a classic word problem using Pythagorean theorem. It says a ladder that is 65 feet long is put up against a wall. The foot of the ladder is 25 feet from the bottom of the wall. Okay, if the top of the ladder slips 8 feet down, then how many feet will the foot of the ladder slide? Okay. So for the first thing of all geometry questions, we just have to draw a diagram. So let's just pretend this is the wall, and we have our ladder right here, which is 65 feet long. And it tells us the foot of the ladder is 25 feet away from the wall. So we have that this distance right here is going to be 25. If the top of the ladder slips 8 feet down, then how many feet of the, this is so hard to speak, then how many feet will the foot of the ladder slide? So basically we have to find this distance D. Yeah, it's a triple, but you can do 65 squared equals, we use the Pythagorean theorem here. Oh yeah, here's the problem. Okay, like if you actually do this, it's not so bad. You can either memorize the triples or you can just do the math. If you actually do this, it should be 3,600. So the square root should be pretty nice. It should go out to 60. Yeah, you can see the problem. It's right there. It's at the top. Okay. So basically, now we know that the value of D is 60. So it's telling us the top of the ladder will slip 8 feet down. So what happens is the ladder slips down a little bit. This slide looks so bad. Whatever. The length of the ladder stays the same since that's logic. And then since it slides down, we know the new height will be 52. 52. Okay, let's just assume the wall is perpendicular to the ground. And then now we just have to apply the Pythagorean theorem again. But at this point, you can notice that both of these numbers have a factor of 13 into it. So it's just a 3, 4, 5 triangle. So we just get, this side length is just 3 times 13. So basically the answer, so this length is going to be 39 now. So it's asking us how many feet does the bottom of the ladder slide? And it's just 39 minus 25, which is 14. Wait, are there any questions? Okay. All right, everyone looks fine with this. So we'll just go to another classic question. It says 2 circles in the diagram. I'll draw the diagram later. But it says 2 circles in the diagram have the same center. And if a line segment has length 9, what is the area of the shaded region? And I'll just draw this real quick. You guys can look at my masterpiece. So basically the question has 2 circles with the same center. Oh yeah, look at that. Okay, let's just pretend those are both circles. And there's a line segment that perfectly touches the inner circle. And we're told it has length 9. And that's all they're telling us. Oh, wait. Also, the shaded region. And what color? The shaded region is just the region in between the circles. So in the question, this is the shaded region. Wait, that's going to be like annoying, but whatever. It tells us, so what we have is this line segment has length 9. Oh, I forgot to mention this, but the area of a circle is just pi r squared. And r is the radius. So if you have a circle with a radius of r, the area is just pi r squared. Yeah, 9 is not the radius. We have to find the radius of the two circles. I'm just going to point this out. So if we want to find the area of the shaded region, what we want to do is find the area of the larger circle subtracted by the smaller circle. So let this be the radius of the larger circle. And we can let this be the radius of the smaller circle. So the smaller circle will have a radius of r, and the larger circle will have a radius of capital R. So what we want to find is pi capital R squared subtracted by pi smaller r squared. Right? Just pi r squared minus r squared. But since right here we have a right angle, we can use the Pythagorean theorem to find capital R squared minus small r squared. So the capital R squared minus small r squared is just going to be this length right here. Sorry, the shaded region kind of ruins it. Let me just, there you go. And then this length is just equal to 4.5, since it's exactly half of the length of the line. So we have r squared minus r squared is equal to 4.5 squared, or it's just equal to 81 over 4. So finally, we multiply by pi to get our answer. And the answer is just 81 pi over 4 is the area of the shaded region. That makes sense to everyone, right? Okay. There's also a small trick you can do for this question. Like, I wouldn't recommend doing this trick unless you're confident that it works. So this question never tells us the radius of the smaller circle, of the smaller inside circle. So what we can also do, we can assume the smaller circle has radius 0. So like we can just pretend the smaller circle doesn't really exist. And then we can just draw the line with length 9 here. And the shaded region is simply the whole entire circle, which can just be found by pi times r squared. And this is just like a shortcut you can use, but I wouldn't really recommend it on like a lot of questions. Okay, let's go on to the next one. Oh, I'm gonna have fun drawing this diagram as well.
Oh. My dad makes me redo old AMC8s, and I think I did this one already.
Wait, this question?
Yeah,
Or the last one?
this one, because my dad makes me redo AMC8s for some reason.
Oh, this one's from an AMC 10 though.
Oh, okay, never mind.
Okay. I think you might learn a thing or two from this one.
All the AMC8, AMC10 questions look the same now.
Yeah, once you do a lot of them, they start to look similar, which is a good thing because then you're comfortable solving them. So this question begins, let AB be a diameter of a circle and let's just first draw a circle first. Oh God. This is why I need to get better at drawing stuff. Okay, we're just gonna pretend there's a circle. And then let AB be a diameter. And it says let C be a point on AB so that 2 times AC is equal to BC. So C is going to be like somewhere over here. So that BC is double the length of AC. D and E be on points on the circle such that DC is perpendicular to AB. So let's just draw D first. D is going to be like right here. And then let the center of the circle be here. It says DE is the second diameter. So E is just going to be the opposite point. And it says, what is the ratio of the area of DCE? So this triangle right here is the area of ABD, which is this triangle. Okay, so what we're going to do is we want to try and find the area of DC and ABD first. And to make our calculations easier, we can assume that like the radius of the circle is 1, since it doesn't really affect the ratio, and it helps us compute stuff better. So let's just assume the radius of the circle is 1. So we have, let's call the center O. And we have the radius of the circle is 1. So since AC is exactly half of BC, we know that the length of AC is just 1/3, and the length of CO is just 1/6. I mean, we don't have answer choices, so how do you know it's C? Okay, so to find the area of DCE right here, we want to find the base times the height. So we can, if we choose CE to be our CD to be our base, if we choose this one to be our base, the height we have to, one sec, we have to extend BC and draw the perpendicular. So we want to find this distance, h, which is the height. But if we draw the perpendicular from E to AB, we see that this triangle, DCO, let me use a different color to make it easier to see. We have that this triangle DCO is congruent to this triangle. These are congruent triangles. So we know that this length is also 1/6. So we know that the distance of H is just the sum of these two distances. It's the sum of CO and this distance right here. That's equal to H. So the area of DCE is just B times H, or it's just over 2. Or B times 1/3 over 2, or just B over 6. Yeah, I'm gonna ignore your answers because like, what's the point? So I guess like 1/3 is right, but like, just wait until like we're done solving, okay? All right. So the area of DCE is just gonna be B over 6. And let me remove some clutter so when we find the other area, it'll be easier. Now we find the area of, what's the other one they want? They want the area of ABD, right? Oh, so let's just write, this is the area of triangle DCE. So we want to try and find the area of triangle ABD. So we can see this length B is going to be the height of triangle ABD. And the base is going to be the length AB. Wait, does everyone see that? Like, this is going to be the height. One sec. Length B is going to be the height of our triangle. And length AB is going to be the base. So to find the area of ABD, we just have B times the base, which is 1, and you divide by 2. So it's just B over 2. So the question asks to find the ratio of the area of DCE to ABD. So what we do is we just divide B over 6 over B over 2, and that just gives us 1/3. Wait, sorry for like the messy explanations. If you have any questions, you can just ask in the chat. Wait, there's always like a lot of different ways to solve geometry questions. But I think this one. Wait, what do you mean a shortcut? Okay, is everyone ready for the next question? Okay, some people are like screaming move on, so. Okay, this one's a number 25 from the AMC 8 a few years ago. It says 1-inch squares are cut from the corners of this 5-inch square. What is the area in square inches of the largest, let me fix this one better, of the largest square that can fit into the remaining space? So what they're talking about is a large square with side length 5, and then 1 by 1 squares are cut from all the corners. So these are all 1 by 1s. So basically the largest area that can fit in the space, largest square that can fit in the space is going to look something like this. Okay, so yeah, some people are saying Pythagorean theorem, but like there's a much quicker way. You can call it a shortcut, but like there's a much quicker way to solve this question. So what we do is let's draw these lines first. I'll let you guys think for a moment, but do you guys have any good strategies for this question? Okay, yeah, Jennifer says find the base of the triangles, which is really good. So since the total length is 5, since the total side length is 5, and each of these small squares is 1, we know the side length of this square right here is 3. So what we can do now is we can find, let me shade in one of these. We can find the area of one of these green triangles, and we can multiply it by 4, and then add in to the 3 by 3 square in the middle. So first, let's try and find the area of one of these green triangles. That's not the triangle. So it's simply just the base times the height divided by 2. So we know that this height is going to be 1, and the base is 3. So the area of the green triangle is just the base, which is 3 times the height over 2. And then since we have 4 of these green triangles, we multiply this value by 4 to find the total value, which is 6. And then finally, to find the area of the whole square, we just add up the area of this blue middle square. And we can easily find that since it's just 3 times 3, which is 9. And then yes, once we add them up, we get 15, which is the final answer. As you can see, this was a number 25 on a pretty recent AMC 8. So basically, if you just get familiar with using these basic tools, you can solve pretty much all the questions on AMC 8 and math counts. Okay, I'll introduce one last topic, or maybe a few more, depending on how much time we have. So it's related with the sum of the exterior angles of a convex polygon. So what the exterior angles are of a polygon are if you extend each of the sides, these are the exterior angles. So there's a nice formula that says the sum of exterior angles is always equals to 360. No, not all the angles have to be equal. It can be any polygon that's convex. So I'll show you a few clever proofs of this, which is pretty cool. The first one, we're just going to utilize the one we've used before. That's sum of interior is equal to n minus 2 times 180. We've established that before. So we've established that sum of interior equals n minus 2 times 180. And what the interior angles are these angles. So all the green angles are going to be interior angles. And all the red angles are going to be exterior angles. So we can see that all these pair up to be 180 degrees. So we have a total of 5. Whose sound is that? Okay, it's fine. Whatever. We can see that there's 5 of these angles that match up to 180. But for a general polygon, it'll be n. So n times 180 is equal to the sum of interior plus sum of exterior. And since we already know that sum of interior is just n minus 2 times 180, we can find that the sum of the exterior is just equal to 360. Okay, that makes sense to everyone, right? There's also another method to prove this that's more clever. Let's just imagine, let's just draw another random polygon. Okay, these lines are not straight. Let's just imagine we have a random polygon. In this case, okay. Let's just pretend like a bug is standing on the side right here. And it's going to walk around. It's going to walk around the entire polygon. The exterior angles right here are simply the degrees. It's simply the angle of each turn that the ant makes. So like once it makes a turn and it goes here, it turns this many degrees. So we know that once the ant walks completely around the polygon, that's the wrong color. Once it walks completely around the polygon, it's gonna have to go in a complete loop. And since the loop has 360 degrees, we know that the sum of the exterior angles is just 360.
I told you to run.
Yeah, hopefully that's the shortcut you're looking for, David. Okay, so for like the last 5 minutes of class, we're just gonna prove some like basic area formulas of other figures that you might see in some tests. So we have like area of a trapezoid. So the area of any trapezoid, which has two bases B1 and B2, and has a height of h. We have the area is equal to B1 plus B2 divided by 2, or like the average of the two bases multiplied by h. Wait, what is this? My bad. So how we can prove this is we can imagine, let's fill in these two triangles right here. Okay, so what we're going to do is we're going to calculate the area of the entire rectangle and then subtract off the two triangles. So the area of the entire rectangle is just going to be B2 multiplied by h. And what we're going to do is we're going to subtract off the areas of these two green rectangles. So if we imagine this length is x and this length is y, we have that x plus y is just equal to b2 minus b1. And then if we subtract off both of the areas, the area of this green triangle is just x times h divided by 2. And then this triangle will have an area of y times h over 2. We can rewrite this as and then since we have x plus y equals b2 minus b1, we can just rewrite this as h times b2 minus 2. And if we just simplify the algebra a little bit, we'll have h times h times b1 plus b2 over 2. And that's basically how you derive the area of a trapezoid.
Because when you notice the 7, you can tell that, yeah, that's what I thought.
Okay, sorry about that. Okay. So that's basically all we have for today. Do you guys have any questions about today? Okay, if you guys are good, then you guys are free to leave. Have a good night.